All right. Good morning, good afternoon, good evening, everyone. Thank you very much for joining us today for our webinar called The Driving Force Behind Advanced AI, presented by CDW and NVIDIA. My name is Michael Carnevale. I'm a manager in our product and partner management organization at CDW Canada. I'll be moderating today, which means that, once the presenters are up, I will be hanging in the background, kind of facilitating any questions you have. If you would like to ask questions, please feel free to include them in the chat. You'll see the chat box on the bottom right, I believe, of your screen. And you can just put them in the general chat, and then we will leave room for questions at the end of the session. So as mentioned, we're talking advanced AI today, and we have a couple of excellent presenters for you. I will introduce Griffin and Michael shortly. But first, I'm going to take a few minutes just to talk a little bit about CDW. So, very exciting times at CDW. For those of you that don't know, CDW acquired Scalar Decisions in 2019. So what does that mean? For those of you that didn't work with Scalar or were not aware of Scalar before, or for those on the other side who've never worked with CDW Canada, January 1st of this year, the two organizations came together, and it is super, super exciting. We now have, the experience and the expertise to help you all solve your toughest IT problems. CDW Canada in the past, very, very good at procurement, delivery, and relatively good at helping you kind of design a little bit of those, those more complex problems. Scalar was the other side of that. Very, very good at delivering the services that you needed to help you with those tough problems. So we now come together and we've got it all in one organization. So we can consult, design, procure, we can deliver those services, and we can also help you better understand things like advanced AI and how it can help your business. So if we look at this kind of milestone chart here, starting all the way back in 1984, and those of you who've attended these before have probably seen this, and I'm not going to spend a ton of time here, right? But I do want to highlight a couple of things. We have been around for over 35 years. CDW has been an organization, a successful organization for over 35 years, and you can kind of see the revenue tracking up to the right consistently, even during difficult times. So we're really, really proud of that, and I think that speaks to the level of commitment from leadership across Canada and the US and globally, and the decision-making ability of those leaders, like I said, both in the US in our head office in Chicago, locally here in Toronto, and around the rest of the world. A couple things I want to call to your attention. CDW Canada joined the Canadian market in 2003. Over the last, 17 years, we've continued to grow, and I've been fortunate enough to be recognized as the top solution provider in Canada, several times over the last couple of years. Very exciting. And then, as I mentioned, 2019, we made the decision to acquire Scalar Decisions. So, with that, we significantly expanded our footprint across Canada with, offices right across the country. And this joining of forces also brought us that breadth of technical expertise and that services portfolio that I touched on a little bit earlier. We can now offer, you, our customers, that full span of solution and services, which we are absolutely thrilled about. You also see that we had another key acquisition in 2019, Aptris, which is probably the largest and most well-recognized ServiceNow partner in the United States. So that was also a very exciting acquisition in 2019. And actually, just earlier this month, we announced another acquisition. EGNW is a US-based cloud-native services provider specializing in DevOps and cloud automation. So you can see where CDW is going, right? We know that we have to really be able to serve in those specific areas, and we're making those kind of moves to do that. And today we're sitting on, the top, the Fortune 200. I think we're at it's at 189 right now. I think I've got it on the next slide. And, we're super proud of that success and also that financial stability. I think this slide does a really good job of just kind of showing CDW globally, and I'll touch on a couple things again. That international coverage, you can see that bottom center there. We support over 250,000 customers globally in 150 countries across the world. And we have offices in, not only Canada and the US, but the UK, kind of mainland Europe, South Africa, Singapore, Australia. So if you have, if you are a global organization, we can support you on that level. And we're obviously very, very proud of that. Here in Canada, 17 years. I mentioned it previously. We've been able to thrive in the Canadian market and serve you, our customers, in any way that we possibly can. One other thing that I wanted to highlight, right up in the top there, we work with over 1,200 partners, right? And those are not just kind of the traditional partners. We've got a lot of emerging partners who we have decided to partner with to provide some of that kind of bleeding edge technology and some of the solutions that that are relevant now and will be relevant in the future. So yes, exciting times for sure. And if we look at things a little bit more locally here in the Great White North, so over 900 coworkers across Canada, and a third of those being technical in nature. 9 offices across the country, as well as a SOC and NOC locally here in Ontario. $1.2 billion in revenue at the end of 2019, a large number. And like I said, I think it just shows the financial stability of CDW. But enough about us. Let's get to why we're all here today. I'm going to hand it over to our presenters now, and here are the 2 folks that are going to be driving kind of this conversation today. So as you can see, Griffin Lacey, Senior Data Scientist from NVIDIA, will start things off, and he'll kind of walk through, NVIDIA's position on AI and a number of the solutions that they have in place. They are a leading player in the space, and Griffin, I think, is an excellent resource to walk us through that. And then Michael Traves, our Principal Solution Architect here at CDW Canada. To put it bluntly, Michael has designed and implemented a lot of the solutions around AI that Griffin's going to talk about, and he'll drill down into a little bit of that as well. As I mentioned, if you have questions, please put them in the chat. We'll be monitoring that, and we will be saving time for questions at the end of our session today. Without further ado, I'm going to hand it over to Griffin. Griffin, all yours.
Thank you so much for the introduction, Michael, and welcome everyone to the webinar. As you've heard, I'm Griffin Lacey, a data scientist at NVIDIA, and I'm going to give a pretty brief account of data science on GPUs, hopefully give everyone a bit of a taste for where things stand today, and tease a few and introduce a few concepts that Michael Traves can expand on a bit in the second part. So to get started, I wanted to introduce this idea of GPU computing and talk about the rise of GPU computing today. For those of you that aren't as familiar with NVIDIA, for a long time, NVIDIA has been tied to the computer graphics space. And really the main problem that was being solved in the early days of NVIDIA was, how can we more efficiently process lots of parallel pixels in just say an image from a video game or a movie or a TV show. And you can imagine the problem is that if you have just say a 4K image that you're rendering at 60 frames a second, and each pixel requires just say 1,000 lines of code to execute, and doing it all sequentially would be terribly inefficient. And this is where GPUs or graphics processing units have been able to solve this problem much more efficiently and elegantly by using massively parallel acceleration. So doing all of these computations that are fundamentally independent at the same time. As things progressed and as time went on, people have discovered that GPUs, although they're intended for computer graphics, are actually well positioned and well suited to tackle problems in things like linear algebra or just general or math problems or physics or chemistry or in fundamental sciences. And this observation was made that in the early days, if we can make our math problem look like a graphics problem, we can actually take advantage of a GPU and things can happen much faster. And over time, this recognition sort of made it into the heart of NVIDIA's engineering development. And out of this was born these software tools, these high-level software tools, which let people not have to think about graphics any longer, but actually just use a GPU as a general computing architecture. And CUDA, which I'll introduce in a moment, was really the brainchild of this. More recently, with the boom of artificial intelligence research and deep learning more specifically, this was such a natural fit with GPUs, as people recognize that really the fundamental principles that are going to help take us into the future of artificial intelligence are really going to require a massive amount of computing power, and really a massive amount of parallel computing power. And with the introduction of these tools like CUDA, as I just mentioned, the fit with NVIDIA GPUs and state-of-the-art deep learning research really went together nicely. And this is why today NVIDIA is sort of branded as the AI computing company, and it has become a central focus of our work. Another way to think of this development is graphically through a look at Moore's law, which was this observation that over time the number of transistors tends to roughly double every year or so. And with that, single-threaded performance, or the performance of CPUs, for a long time predictably improved. And so this meant that when people are doing their research and they want to go faster every year, all they need to do is basically buy a new CPU. And with the advances in technology in that time, their code is just going to run faster. The problem is that ever since about the 2010 mark, we've seen this trend plateau, or more simply die off, and that you can only squeeze so much performance out of these single-threaded instruction sets, and you can only make transistors so small. And so over time, in order to squeeze more performance out of general computing frameworks, this is where GPU computing has really been really important. And so you'll see this in how it's manifested in higher education and academics, and that people are really thinking more about parallel programming as a paradigm to take us into the future. And this is where GPU computing is now so ubiquitous and so commonplace in how people are thinking about advancing science. And as I just alluded to, this CUDA architecture, which stands for Compute Unified Device Architecture, is really the layer that's going to allow the high-level applications and algorithms and systems communicate with the low-level hardware, the GPU. And so CUDA is really a fundamental contribution on the NVIDIA side to how GPU computing has been thrust into the mainstream. And so it's tempting to think about NVIDIA as just the hardware part of the solution and just the GPU specifically, but really NVIDIA is a platform company, and it's about a combination of both hardware and software. So this is a high-level picture of what our platform looks like. If we track through this incrementally, if you start at the bottom rung here of this hierarchy, we're talking about the GPUs themselves. And there are many ways to consume GPUs. You can use can buy our Tesla GPUs, which are intended to go in servers. We have other types of GPUs that are intended to go in things like workstations. We have virtualized GPUs. We have purpose-built AI supercomputers that we brand as DGX, and we have partners that produce their own versions of this. And we have system OEMs that produce things that look like this as well. And we're also available in all the major cloud service providers. And it doesn't matter where you're consuming that GPU resource, it's all going to use the same CUDA interface. And so really what that means is that your code that runs on a virtual GPU or a DGX is going to run the same on a cloud instance. And that's what makes this idea of code portability and acceleration so powerful. Taking one step up from the CUDA layer, we have these things called CUDA accelerated libraries, or CUDA-X. And these are collections of primitive operations that are important for particular applications. So if we look at the HPC space for high-performance computing, there are CUDA accelerated libraries like QBLAST for linear algebra, or QFFT for fast Fourier transforms. Over here on the AI space, we have libraries like cuDNN for deep neural networks, or NCCL for collective communications to help us do distributed deep learning really quickly. Most practitioners today don't have to worry too much about how or why these libraries do what they do, for the most part, people are going to engage or interact with GPUs at a higher level. And so this would happen at the application or framework level on the upper part of this chart. And so if we look in the HPC side of things, we're talking about high-level fundamental science codes like AMBER and AMD or GROMACS or ANSYS. In the deep learning side of things, we're talking about tools like TensorFlow or PyTorch or MXNet. In the machine learning side of things, we're talking about the scientific Python stack or the Rapids ecosystem, which I'll introduce briefly shortly. Basically, as a practitioner today, if you're doing, for example, deep learning research, you're using a tool like TensorFlow from Google or PyTorch from Facebook. You're defining a high-level graph or a neural network, and really all of the hard work and the plumbing to make that accelerated on GPUs is done for you. And so all of the hard work here is the heavy lifting, I should say, is done by CUDA and the CUDA accelerated libraries, but really it's made accessible to a high-level researcher so that if they wanted to do something very custom, they can go program in cuBLAS or in TensorRT, or they can do it in CUDA, but for the most part, they don't need to concern themselves with that. So you don't, the message here is that you don't need to be a GPU expert to take advantage of GPUs today. So focusing just for a moment on deep learning, there's been this large boom in the interest and in the performance of deep learning models as they pertain to state-of-the-art problems that people care about. And these ideas have been around for a long time, but they've gotten a lot of notoriety in the last decade or so. One of the reasons for this was that, in the 2010s and beyond, we've now had a large amount of labeled and unlabeled data that we can use for training. And this is something that has not existed for a terribly long time. As well with GPUs, we've had with the introduction of CUDA and then these large and sort of massively parallel accelerators available to a lot of people. We've had enough compute to try these really large hierarchical composable models. And then finally, there's been a bunch of fundamental contributions, many of which came from Canada, that really cracked open the case on understanding how, once we theorized that we should be training these really, really deep, really complicated models, how exactly we should go about doing that. And so it can't be overstated how important the academic side of things was in pushing this forward. And so as it stands today, if you're a researcher who's concerned with AI or deep learning specifically, you're going to be going and installing TensorFlow or PyTorch. And then inherent in the framework itself is going to be an understanding of NVIDIA GPUs or of CUDA. The way to think about this is that all of the semantic language and plumbing that's necessary to take your PyTorch or TensorFlow code and run it on GPUs is already going to be baked into the framework itself. So you don't have to think about this at all. You just have to make sure that CUDA is installed on your system and everything else, and you have a GPU available, and everything else is, for the most part, going to be taken care of for you. You'll just have to set a flag or a parameter that's going to say, I want to run my code on CPU, or I want to run my code on GPU. And on GPU, it's going to run a lot faster. So similarly, on the machine learning side of things, which is a more broad, general collection of algorithms and techniques that people are concerned with, there's a similar analogy to be made in that if people are doing data frame manipulation and they're using a Python library like Pandas, in the Rapids ecosystem, which is an open source collection of tools that are important for data science, there's going to be a GPU accelerated version of Pandas we call cuDF, which is going to be important for people who are doing data frame manipulation. Similarly, scikit-learn is an incredibly popular library for doing machine learning. There's a GPU accelerated version of it we call QML that's available in Rapids. And so this ecosystem is a bit more expansive than what I've made it out to be so far. It's not just cuDF and QML. And in fact, there's a lot of really tightly integrated components that make it so that the entire pipeline for a machine learning practitioner, so everything from preparing your data to ETL, to model training, to visualization, there's likely going to be a component of that that's parallelizable and you can accelerate them on GPUs using a Rapids piece. And so the purpose of today's talk is not to get too much into the weeds of all of what Rapids is and what it can be used for, but just appreciate that the era of GPU support for machine learning and data science is upon us, and it's likely that if what you're doing is fundamentally a parallel workload, that it can be accelerated with GPUs. A thing to mention here that was announced recently is that Spark 3.0 is going to be more deeply integrated with GPUs. And the purpose here is that we want people to take advantage of GPUs no matter what high-level application or framework they choose. And so here, a lot of the foundational work that was done inside of the Rapids ecosystem can be borrowed and leveraged to make, for example, Spark 3.0 very GPU aware and GPU friendly. And so if anyone is familiar with the current workloads in Spark 2.x, some of what you would want to do in your machine learning pipeline is GPU accelerated today, but not all. What the goal is, or the vision is for the future, is to have every part of your pipeline that can be accelerated with GPUs. We want that to be enabled. And so this is going to make it so that Spark 3.0 is going to make available to you a single pipeline from ingest to data prep to model training that's all going to be consolidated and simplified with GPU awareness. So moving on, now that we've sort of understand where things stand with GPUs today, there's been an exponential growth in the amount of computing demand from a fundamental AI perspective. And you can measure this in many different ways. You can measure this in the amount of data that is available to us in terms of zettabytes that is generated every year. You can look at all of the papers that are submitted to high-profile AI conferences, such as NeurIPS or CVPR, or you can just look at it in the rightmost graph here in terms of all of these state-of-the-art models that are important every year. And you see on the x-axis, we have a measure of time. All the points in this graph represent an individual model that had a substantial contribution to the AI community when it was released. And if you measure, and this graph is a bit hard to digest, but just understand that it's a measure of the petaflop days. So the number of, if you had available to you a petaflop of floating point operations every second, so that would be, I believe, a quadrillion floating point operations every second. If you have a computer that was able to compute that, this is the number of days that it would take to train one of these models. And so in the early days, obviously, with something like AlexNet, if we had a petaflop of performance available to us, we could train AlexNet on the order of minutes. But at the time in 2012, that amount of compute wasn't readily available. And so AlexNet took close to a week or so to train. And so we can see over time that models are becoming more complicated, more sophisticated, and the amount of compute that is necessary to train them in a reasonable time is growing. And similar to the AlexNet example I just gave, the understanding of how to take those models and distribute them among whether it be many GPUs or many nodes with GPUs on them has been well understood for a while. And the way in which we can distribute deep learning, whether it's distributing our model or distributing our data, has been well understood and is well articulated in the high-level frameworks that people are using today. And so if you're using TensorFlow or PyTorch, as I just mentioned, there are going to be optimizers and high-level tools that are going to allow you to do distributed deep learning quite easily. The requirement on your end is just that you have access to a system with multiple GPUs, or in the extreme case, a large cluster with multiple nodes that have multiple GPUs on each node. And so over time, to address this need to be able to take a distributed deep learning model and train it in a reasonable time, we have introduced our NVIDIA's own brand of AI-specific supercomputers called DGX. And what was recently announced was the latest iteration of this called DGX A100. And A100 here is actually the name of the new architecture, or the new GPU based on Ampere's A100 architecture, of which the DGX A100 has 8 of them. Each A100 GPU having 40 gigs of GPU memory for 320 gigs of total high bandwidth memory. We have this proprietary interconnection called NVLink, which allows these GPUs to talk to each other in a very high throughput way. about 10x in the latest version of DGX A100. This is about 10x the bandwidth of PCIe Gen 4. And so, as I mentioned, one of the key principles with distributed deep learning is allowing these GPUs to talk to each other very quickly in the data parallel way. It's changing or making available all of your data set to each of the GPUs in your system and then averaging the results, or in model parallelism, it's actually breaking apart your model and passing them to GPUs and then having some sort of synchronization across them. But basically, as you distribute your work and as you scale up, the ability for your GPUs to communicate with each other becomes very important. And so these DGX systems, of which Michael Traves will talk a little bit more about, are thoughtfully designed in the way that they are engineered for AI, for deep learning specific workloads. So there's a whole array of really interesting features I could talk about with A100, and I don't have time to exhaustively cover them. So I wanted to mention two that I thought were especially interesting. The first was this idea of these new TF32 tensor cores on A100. For those of you who are familiar with what tensor cores were as they pertain to previous generations, just understand that, or if you weren't familiar with that, just know that the ability to take less bits to run your computation, so to use, instead of maybe 32 bits of floating point precision, but using instead 16 bits of floating point precision to compute your weights and your activations for your neural network, that can have a profound impact on performance. And so tensor cores were originally created with this idea that if we know that we can get away with fewer bits and we can train to a similar accuracy, and we know that for neural networks we're doing mostly, for very state-of-the-art models, we're doing mostly matrix multiplication accumulates, we can actually make these tensor cores, which specifically do in the early days FP16 matrix multiply accumulate operations very quickly. And the impact of this is that if you are using a model, and it's to say in TensorFlow or PyTorch, and you have a GPU on your system that has tensor cores, you can just enable FP16 on your model, and then all of a sudden your ability to train is going to be significantly improved. Now, one thing we've noticed is that while FP16 in theory should be very helpful for a lot of people, some researchers were a bit hesitant on using it, in that it introduced an additional parameter that they had to play around with in their models. You can think of it as introducing an additional variable. And for researchers who are so accustomed to already juggling many variables and many free choices in their model, sometimes it seems like a bit of a too much overhead in introducing one further for using something like tensor cores. And so TF32 is sort of a best of both worlds in terms of it's a combination of the way that FP32 and FP16 numbers are represented. So it actually uses the same range as FP32 and the same precision as FP16. And it provides this new format, TensorFloat32, TF32, which makes it so that you don't have to change your code at all and you realize a tensor core speed up. And so this, I'm being a bit convoluted in my explanation. Just understand that with TF32 on A100, your researchers will be able to realize a huge speed up from training, similar to what we've seen using traditionally FP16 with tensor cores, but they are not going to have to make any code changes. It's going to happen all behind the scenes, which is, to me, a very powerful idea. Another really important contribution from A100 was this idea of multi-instance GPU, or MIG. And to say it succinctly, this is a way to partition GPUs or A100 GPUs in up to 7 instances, so that you can do a number of parallel simultaneous workload execution with a guaranteed quality of service. And this is very different from how people have been partitioning GPUs up in the past. The main way in which in the past people were able to take one GPU and give it to a number of different people was to partition the GPU resources temporally. So you would give people slices of the GPU computing resources over time. But the way that this is partitioned with MIG is actually spatially. So if you have, to say in this example, 7 different MIG instances running on an A100, you can have 7 different people having their own CUDA cores, having their own L2 cache, basically having an isolated GPU instance, which is going to be much more flexible and much more powerful in trying to find the right size GPU application for a number of different people. And so in the extreme case, because you have 8 A100s on a DGX A100, you can have up to 56 different MIG instances. To quantify the importance of these resources, you can look at for AI acceleration. So from BERT large, which is a large transformer-based NLP model, if you look at the speed up from the light green to the dark green, which is V100 to A100, for FP16, we saw about a 3x improvement, which is a substantial speed up in how fast we can train BERT large. So this is measured in number of sequences per second that we can process. But you'll see for FP32, so for people who never use tensor cores, for people who are using FP32 workloads, the introduction of TF32 has allowed us to experience a 6x improvement in speed up. And so this is a substantially important effect for the average researcher who maybe wasn't already taking advantage of tensor cores. And on the MIG side, this can be incredibly important for things like inference. So not for actually training your models, for actually deploying them for an inference workload. We see that the capability of one MIG instance, which as I mentioned, is in this example is 1/7 of an A100. We actually see a similar amount of performance using a BERT large inference model with a single MIG slice to what is possible in an entire V100 GPU. And so to extrapolate this further, using 7 MIG instances, so 7 instances of a BERT large inference, we actually have 7x the inference capability that was possible on V100. And it's important to mention that not only are all these contributions happening at the hardware level, but as I mentioned, NVIDIA being a platform company, the software is so critically important to making all of this work properly. And NGC, NVIDIA GPU Cloud, is the way in which NVIDIA distributes this software to people. So this one big important element of NGC is our container. So we have a TensorFlow container and a PyTorch container and containers for all the fundamental science codes I've already talked about and many more. In addition, we also have a series of trained models. We have Helm charts on NGC. We have a bunch of very powerful AI toolkits and SDKs. And all of this work that we've done on NGC is freely available to people to go and download and run on their DGX systems. And they can also run, in addition to DGX systems, they can run this in the cloud. They can run it on-premise, as I mentioned, or a hybrid version of that, or they can go and deploy this on the edge for an industrial or a medical or a retail application. So I won't dig too much into NGC, although I would encourage anyone who hasn't been exposed to it yet to go check out ngc.nvidia.com and see all the really important contributions we've made to the software on those Docker containers and train models. So the last thing I'll mention as it relates to performance here is that with NGC, we deliver, for example, with deep learning frameworks like PyTorch and TensorFlow, we deliver a new version of them every month, which is going to be more and more highly optimized for the hardware that we test on. So what I mean by this is that over time, a fixed piece of hardware like a V100. So if we look at in 2017 when we released a V100, the performance across a basket of top apps. So we're talking about Amber, Chroma, GROMACS, Milk, NAMD, PyTorch, Quantum Espresso, Random Forest, and TensorFlow and VAST. If you look at the performance in 2017 of V100, it was about 2x that of a P100. Well, in 2018, with all of the the incremental improvements we made to all those codes and distributed them through NGC. Now V100 was 3x faster than P100. In 2019, that improved further to being 4x faster than P100. So you see the same GPU, the same architecture over time becomes faster with all of these software improvements. And you see where we stand today with A100, we're 9x faster than we were with P100 4 years ago. And so it can't be overstated how important these software improvements are to the performance of these systems over time. And I would be remiss to not mention that in those who have been followed the news and have seen the NVIDIA acquisition of MELLANOX, networking is now a hugely, and it has been a hugely important part of us building and comprising these large clusters of GPU resources and making sure that when you're distributing your work across these nodes, that the throughput or the ability for the nodes to communicate with each other can keep up with the need for high performance in your application. And so you'll notice in DGX A100 that we have this incredibly powerful setup of these CX6 network adapters from MELLANOX. So we have up to 10 CX6 cards in these systems, which is just an incredible amount of total throughput over InfiniBand or Ethernet that can make it so that if you are building a high performance cluster and you intend to use this cluster to distribute these large workloads across, this is going to make sure that networking is not going to be the bottleneck for your work. And finally, before I pass it off to Michael Traves, I just wanted to introduce this idea briefly, which he will expand on more, which is that taking these DGX systems and building data centers out of them, building what we would call pods, which are basically collections of these DGX systems with an architecture that defines how the storage is architected and networking. DGX pod has been a really sort of fruitful exercise for NVIDIA to understand how to go and deploy these large data centers efficiently with high performance and with sort of the most amount of simplicity and support so that we can make sure that all of our customers who are doing this for themselves are successful. And with that, I will pass it over to Michael Traves.
Good afternoon. Let me just put this in presenter mode here. There we go. So yeah, I'm Michael Traves. I'm with CDW, and I'm just going to walk through some of the solutions that have been touched on by Griffin here, and how we actually take this and kind of put it into practice. So looking at AI from a workflow perspective, we've touched on this in terms of taking data, ingesting data into the workflow, into the model. This might be called machine learning pipelining. Taking that data, cleaning the raw data, preparing it for training on that data, iterating through the training model to getting the results more and more accurate as you progress. And then once you're satisfied with it, optimizing it and deploying it from an inferencing perspective. So this kind of takes us through the analytics, the training, and into inferencing, which is really the production. And these are different types of use cases leveraging this infrastructure, and how you would leverage the technology to do that at each one of these stages. So depending on where you are in your kind of journey with AI, you might be in the experimentation phase. You might have some GPUs under your desks and workstations. You might have some graphics cards you're leveraging for doing AI on the off hours. But as you progress from idea and you want to actually start implementing things and doing more training exercises, you're looking at faster and more GPUs to do that kind of work, and that's where some of the DGX systems come into play. The DGX family is DGX1, DGX2, now the DGX A100, which is really that next generation platform people are implementing. And again, whether you look at one with 8 GPUs in it and try to take that, break it into potentially up to 56 megs and then share that between all your data scientists, or whether you're looking at deploying multiples of these into a pod, it's really taking that infrastructure and creating a shared service for your data scientists and researchers to use, and to run multiple types of workloads on it. So as I mentioned, training, inferencing at scale. And then once you get into doing inferencing, where do you run that? Typically, training is a very compute-intensive type of job. It runs for hours or days, depending on what you're actually doing. So very high utilization on the systems. Whereas inferencing is really, the end result. It's kind of on demand. You want to be able to scale that up and down based on how your users are actually accessing it. So inferencing typically at the edge, a good use case for cloud as an example. Whereas training, if your data is in the cloud, that's great. But if you're going to be running those instances for continuously, they can be very expensive. So these are kind of some of the decision criteria you need to make about what you're going to run and where you're going to run it. But this is how you would progress through that. And what the AI software actually encompasses. So we've talked a little bit to this, but starting at the foundations, GPUs, we want to take a lot of the work done that NVIDIA has done at containerizing all of the components necessary to run AI and building your frameworks, support the application stack, and then deploy that these days using Kubernetes. And I mentioned Kubernetes here as a way to kind of take those containers, deploy them into a framework or for job orchestration that allows you to run them really anywhere and on any target environment. So with Kubernetes, you have the ability to deploy those on a single node, on multiple nodes through scheduling, and deploy them on whether you're running Kubernetes locally or leveraging one of the Kubernetes environments in public cloud providers, or doing it at the edge. It's one job orchestration that you can push out to any environment. The DGX POD software stack is also made available through what I'll touch on in a little bit here in terms of DeepOps. And the idea here is you want to be able to support a pod, which is multiple of these DGX servers, appliances, and do so in a consistent way. So when you deploy one pod, you want to be able to push out all of the software to them and have them be consistent. And you want to do that also from multiple pods, so that you can have multiple environments, possible multiple generations. So the actual management software to push the software instances out, to be able to monitor, alert on it using open source tools like Prometheus, Grafana, and Alert Manager, and to leverage different ways, different technologies, whether it's Slurm or Kubernetes. If you're coming from an HPC background, you may prefer to do things using Slurm for job management as opposed to, say, Kubernetes. And there's different use cases, and I'll touch on those in a little bit. But all of this using technology like Ansible and Ansible playbooks to provide the repeatability and consistency when you're rolling out the environment. So what is DeepOps? I mentioned it here. DeepOps is a collection of tools. There's actually a GitHub page that, if you're interested, you can go there. And really, it's the tools to deploy a pod using NVIDIA DGX to deploy different types of pods. Whether, as I mentioned, you're going to do maybe Slurm or Kubernetes, but to have a consistent management framework, consistent monitoring, and metering of those resources, to be able to do upgrades, to be able to add nodes, and remove nodes from the cluster. So all the automation has been built and can be leveraged for you in your environment, whether that's a single node DGX that you want to orchestrate jobs on, or whether it's a multi-node or multi-pod environment. And this is what that would look like. So from a login node perspective and a management node, that's kind of where the infrastructure to support this runs and allows you to push out Kubernetes nodes or Slurm nodes. Typically, you're going to run one type of orchestration tool on a particular node type, and in your environment, you may run both, and I'll touch on that next. So you're going to do a lot of that over the front end over your 1 or 10 gig Ethernet. But as was mentioned, when we start talking about multi-node environments and multi-GPU jobs, you want to be able to have GPUs talking to each other that may not be on the same DGX node or on the same compute node. So how do you do that? And that's by building out 100 gig, or in the case of DGX2, 200 gig InfiniBand or Ethernet, and enabling those nodes to share data between GPUs very, very quickly. So GPUs can write data between each other's memory. Likewise with storage, each one of these nodes has a significant amount of storage on it. DGX A100 has about 15 terabytes worth of data. on it for scratch space, but you need to be able to get data in and out extremely quickly. So being able to have 100 gig or 200 gig InfiniBand or Ethernet network to support storage connectivity is really important. So you can read that data in and write the result sets out very, very, very quickly and share those across multiple nodes. So I mentioned the orchestration versus job scheduling question. So both of these are supported, and depending on your background, whether you're coming at this from an HPC standpoint or a data science perspective, and they may make more sense. So Slurm has been a very traditional tool set in the HPC space and provides strong capabilities around job management for users. Whereas Kubernetes is stronger in the container space and being able to run workloads distributed across multiple nodes. So you may approach this from one versus the other. And in the case of Kubernetes with Kubeflow, it provides a very easy way for data scientists to leverage their Jupyter notebooks to submit jobs into the cluster. We touched on NGC, and again, this is the GPU optimized software hub. This is what NVIDIA's made a significant investment in building containers with all of the components necessary to run your workloads in, and allows you to run those workloads anywhere on any GPU, whether it's in one of these pods, whether it's on individual nodes, on a workstation, or in a public cloud environment. So a lot of value that this brings to the table. That we encourage our customers to take advantage of. I've seen customers deploy their own workloads and kind of build their own, whether it's on bare metal or using containers, but they haven't done the optimizations as well as NVIDIA has, and of course NVIDIA does iterate on this. So they deploy it themselves, they get the results they expect, then they try it with an NVIDIA container and they get 2 to 3x the performance without even thinking about it, and then they wonder why. And so that's why I encourage, if you're not using them, then please take advantage of it, because this is one of the big differentiators that NVIDIA brings to the table. And then the operator for Kubernetes. So getting into the operator framework now in the latest versions of Kubernetes, it allows you to kind of containerize a lot of the complexities for supporting the GPUs in the containers themselves and deploying that. So there's some additional software capabilities that NVIDIA's invested in to make deployment and management easier going forward. And there's a number of software partners in this space. You may recognize some of the logos, and there's kind of two approaches to what I wanted to talk about here. Is you can look at your own environment. You may be using GPUs today. You may be leveraging different types of GPUs. You may be leveraging different clusters of GPUs of various generations. You might have a cloud environment as well. So some of the tool sets allow you to basically make it easier to submit jobs and determine where those jobs run. So data scientists may submit a Jupyter notebook and say, I need 2 GPUs of this class. Here's my data source. And then the software stack will determine where does it make the most sense to run. And that might be on an on-premise cluster. It might be in a cloud-based cluster. It might be where the data happens to be because it's a significant amount of data. So that's the one software set solution. The other type is, you may want to power the GPU pod, but you may not want to actually make the investment. And that's where you can get kind of GPU or GPU NVIDIA pods as a service in some of the cloud offerings that are really built around with AI in mind, as opposed to a generic public cloud provider with AI capabilities. So what is the pod reference architecture? The idea is, let's bring together all of this technology and really address, one of the 2 big barriers to AI. On the one hand, you've got to bring people in, the data scientists, and develop the expertise around how to manage the data and get value from it. And the other, you actually have to have the infrastructure for them to use to be productive. So the reference pod architecture takes that second barrier away from you. You don't have to be experts in infrastructure. What you need to do is kind of look at one of the reference architectures that suits your specific needs, and build that very programmatically, from the documentation and working with partners. And really what that does is because you're building something that's known from a support perspective to handle a certain amount of workload and be implemented a certain way, you're not figuring things out, and you can really shorten the time it takes to get to value. So scalable performance, faster, simplified deployment, leveraging the reference architectures, and all of these are supported by NVIDIA. So if the reference architecture exists in partnership with NVIDIA, then you can get support from them on the solution stack as opposed to having to try to piece it all together yourself. This is all based on the reference architecture. The reference architecture is all based on NVIDIA's DGX Saturn V, the supercomputer, which right now is up to about 2,000 DGX systems. And the concept of a pod, which is a certain number of racks hosting the DGX nodes, the associated storage and high performance networking to go with that, and then the software stack that I've talked about. And today, the reference architectures exist from a variety of storage vendors that have taken it upon themselves to take the NVIDIA DGX pod design and incorporate their storage solutions into that, leveraging InfiniBand or 100 gig Ethernet, and providing typically all flash as a way to get data in and out very, very quickly at scale. So tens to hundreds to terabytes to petabytes worth of capacity. And the DGX Saturn V evolution, we talk about the DGX pod and now the super pod, incorporates multiple generations of technology. And that's important to understand as well, is whether you're starting with GPUs and workstations on your desk, or whether you're starting with the A100 today, one of them, if you need to scale, you can do so, and you can fully integrate all of this technology using all the tools that we've talked about. The SuperPod, I think it was recently released a couple of months ago. But just to give you an idea of scale, we're talking about 700 petaflops of AI, 140 DGX A100 systems. So there's only 140 of them out of that 2,000 that's part of the solution today. Leveraging 200 gig for their interconnect, 4 petabytes of storage, and there's already 3 reference architectures available from storage vendors with more to follow. And talking about the whole implementation timeline, I mean, shrinking it really down from months to a week, but basically down to days by following the reference architecture. So order everything, integrate it all. You may pre-integrate it into the racks, ship the racks, and have it fully implemented. And these are some of the vendors that are part of those reference architectures today. Okay, and this really just brings it all together. We're talking about the infrastructure partners, the compute, the networking, the data center, whether it's your data center, whether it's a co-location facility that runs this for you in the cloud, whether it's AI as a service or a public cloud consumption model. It's really bringing all that together along with the software, the partnerships, and the tools to support you on your journey. So what does CDW bring to the table? I mean, really it's the expertise from an architecture design and delivery standpoint. It's understanding the GPUs, DGX pod, whether you want to build that on-prem or in the cloud. We can help you with making those decisions and also help you ensuring your workloads are portable between them. Dedicated lab and pre-staging environments, consolidating all of this at staging center so we can build it and ship it to you pre-built. The extensive experience that we have in the HPC space around data center planning, power cooling, cabling, all the high-speed networking and optics. I mean, we've done many, many very, very large HPC and projects with customers in my career at CDW. So it's certainly a core competence. And then some of the things just to consider. I mean, where is your data? I mean, data gravity plays a large part into this. We have customers that kind of look at it and they have an idea about what they want to build, where they want to build it. But if you're dealing with tens to hundreds of terabytes to petabytes of data, that may constrain you as to where you can actually build this, whether it's on-premise or looking at a cloud provider. Data governance, same kind of idea. As you ingest all this data, where is it coming from? How much of the data do I have to deal with this particular issue on? And does it make sense to put it on a public cloud? Inferencing typically is customer facing. So looking at high availability disaster recovery, and whether you build out or push that to a cloud environment that might have a lot of those capabilities and a global front for customers to hit. And the power and cooling. I mean, many customers struggle with the fact that DGX2 used to be 10 kVA, now the DGX A100 is 6.5 kVA. That's still a lot of power and cooling requirements per rack, or per appliance, let alone per rack in many environments. So can you build that? How do you build that? How do you build the power cooling around it to support it? Water cooling strategies and HPC environments are done a lot of those builds for customers. Or do you have to look at a colo? And that feeds into the whole thing around cloud first. Many customers have the cloud first strategy, and they have to justify why not. And in many cases, you may end up running both. That's what I talked about. If you're leveraging compute 100% of the time with GPUs, it makes a lot more financial sense to run that probably on site, probably where your data is, than trying to run cloud instances at 100% utilization. It's just not cost effective, but it does make sense to leverage cloud for things like inferencing. So you got to look at all that kind of stuff. And lastly, then obviously, I think consuming AI as a service, Jupyter notebooks, Kubernetes from the desktop all the way out to the edge versus Slurm, understanding when to use each. To make it typically Slurm for training, Kubernetes for inferencing, serverless functions, and on-prem versus cloud. So a lot of things to think about as how you actually consume AI. And I guess this is my last slide. Again, I worked with one customer, a very large financial institution, and they've gone through a couple different generations, 3 or 4 different generations of NVIDIA technology, but we started by helping them build out a pod using DGX1's reference architecture with a pair of switches and high-performance flash-based storage. We've since implemented a second pod using DGX2 and migrated the first pod into it using a leaf-spine topology, and also looked at moving, that was the R&D kind of environment, helped them with their inferencing requirements and building out a separate environment for that with OpenShift. And then at the same time, we automated the whole thing, so when they need to roll to the next node, they can use their Ansible playbooks to do so. And then down the road, we'll hopefully be doing the same thing with the A100s. And I haven't left a lot of time, but we're now into questions.
Thanks, Michael. Thanks, Griffin, for walking us through that. We are almost right up against time, and I know we do have at least 6 questions. I do appreciate everyone who did submit a question. I'm going to just kind of start going through these. I understand that people potentially have hard stops, but we're going to try to get in at least a couple of these in the next couple of minutes. So I encourage you to stick around if you can. Yeah, why don't we just dive in and not waste any more time. So I'm going to start with the first question that we got, and this can go either to Michael or Griffin or both. Can you provide insight into AI projects that we have completed together with specific examples? I feel like, maybe the example that Michael just gave kind of covers that a little bit. Griffin, Michael, what do you guys think? Is there anything else that you want to add to that, or do you think that that example is good enough?
I mean, that's certainly one of the larger examples and kind of multi-generational that I think is important, and having to deal with, where you start adding pods and scaling the pods out, looking to the future. And so, yeah, I think that it kind of addresses that. The important thing is you can integrate multiple generations of GPU technology. You don't have to start at a pod. You can start, at a node and scale it from there. And the power of that DeepOps framework for deploying all the infrastructure supports that.
Thank you. Next question. How can we leverage AI and machine learning with NVIDIA to grow business and monitor security? A timely question, I'm sure.
Yeah, I think just seeing the question in front of me, it's hard to know exactly what they mean by security and growing business. But I would say in general, the way to use AI and machine learning with NVIDIA is to either connect with it at the platform level. So the way that most people are using NVIDIA is by going and getting GPUs and then installing the common AI frameworks, and then using the integration of NVIDIA GPUs in those frameworks to research ideas and to test experiments. There's also, though, I should mention, many SDKs and libraries that NVIDIA puts out to make solving these types of problems a lot easier. So I would encourage anyone who's not familiar with the NVIDIA SDKs. We've got some in computer vision that are important, obviously, for monitoring security, but we've also got some in natural language processing and in recommender systems. I would encourage people to go and do maybe a quick Google search or to look at our latest CEO's GTC keynote presentation, where he talks about some of the latest SDKs in these areas that might be important. But long story short, the best way to leverage AI and machine learning with NVIDIA is to start using software that is NVIDIA friendly and GPU enabled. So that's either the open source, the community code like TensorFlow and PyTorch that a lot of people are using, or in other cases it can be the SDKs that we put out ourselves.
Thanks, Griffin. How much processing is required for conversational AI?
So that's a harder question to answer because conversational AI can mean so many things. I would say if those who are paying attention to my deck, I had a slide that did an overview of a study that OpenAI put out about these measure of state-of-the-art models in terms of petaflop days. So basically, how fast would I need a computer to be in order to train a state-of-the-art model in a reasonable time? And one trend you would notice on there is that the requirements for NLP in general, so natural language processing, whether that's text to speech or audio transcription or natural language understanding, these usually involve really large data sets. We're talking about like a Wikipedia corpus or a huge corpus that has been collected privately at a company. And those models, if you're training them from scratch, are on the higher end of computational requirements today. We're talking about anywhere from 1 to 10 petaflop days. So if you want to train a model in a reasonable time, of which reasonable to me would mean a day or less, you're going to need a petaflop or more of performance in your GPU cluster to do it reasonably. I think the opposite answer would be if you have just a single, just say like a GeForce card that you're using for gaming and repurposing it for AI, and you're trying to train like a BERT from scratch. It's going to take you an unreasonable amount of time to get insight on that experiment. So I would say that in general, NLP is on the end of more sophisticated models today with larger data sets. And for those, I would say the minimum starting point is, typically speaking, at least a cluster with more than one GPU.
Great. Is it possible to cover examples of the deep learning frameworks and tools for DGX-1?
I'll answer that very quickly by saying that all of our DGXs use the same software stack. So all of the NGC containers and all of the frameworks that we've described, that's all just going to use CUDA, and that's going to be backwards compatible with DGX, with really any other NVIDIA tools that we're putting out. They will have features that are relevant to newer architectures like DGX Ampere, but they're all going to be completely backwards compatible with DGX-1.
All right, let's see if we can squeeze in 2 more here before we wrap up. We still have a number of attendees on the line, so let's see if we can power through them. Do you have the facilities to leverage existing, i.e. legacy GPU technologies into compute clusters, and is that a viable option?
So yeah, I think from that perspective, absolutely. I mean, it's really a question of how you orchestrate jobs to be deployed on those older platforms, and how you include them. So like not knowing what they are, maybe they are sitting in a workstation under somebody's desk. But a couple of the different technologies that I talked about from a software perspective, one that I know more is Converge.io. There's another one, Iguazio. Both provide kind of the framework for, say, data scientists to submit jobs and give it a kind of, I guess, a policy and define what that policy or job requires. So give it a gold, silver, bronze type of GPUs, things like that, and it will then go out and run that job on an asset that makes sense for. So you could incorporate older generations of CPUs, existing servers with GPUs in them, into that environment, and allow that orchestration tool to run jobs on those environments. So that it absolutely can be integrated. You know a little bit more about what we're actually trying to integrate, but it's possible. And I think the portability of being able to run a container anywhere in your environment, really that's the only requirement is in these types of solutions from an orchestration perspective. It's all the same software stack, therefore it should be able to run anywhere.
Excellent. Let's do one more. What would be the next generation GPU for cloud computing?
Yeah, in a sentence, our newest Ampere architecture, A100, is being integrated into cloud computing resources. So basically, if you're already using cloud computing today for GPUs, just pay attention to the latest announcements that come from NVIDIA or those cloud partners, and they will have full access to all of those the next generation GPUs as they become available.
Awesome. Thanks, Griffin. All right. Why don't we wrap this up? Griffin, Michael, thank you very much for walking us through this today. We really appreciate the insight. And thanks to everyone who's still on the line for joining. If you do have any additional questions that we either didn't get to or you didn't have a chance to ask, or if you want to schedule some time to have a more detailed conversation, you can reach out to your account manager at CDW or your account executive, whoever you deal with on a regular basis, and they would be happy to set up some time to dive in a little bit deeper. You will receive a copy of what Griffin and Michael presented today. And we are also going to get you a copy of an NVIDIA white paper called the DGX A100 Super Pod. So stay tuned for that. And yeah, I think that's going to be a wrap for today. Thanks again for joining, and we look forward to seeing you on the next one. Have a great afternoon.